Welcome everybody, and happy Thursday. Thanks for joining us for another episode here of Coffee with Caleffi. My name is Cody Mack, and I'm one of the trainers here at Caleffi. And today we've got an awesome guest speaker by the name of Mark Eatherton, and he is going to be talking about domestic hot water delivery systems and some of the things that you may have experienced, but you couldn't quite put your finger on, and how to troubleshoot them and make those systems work as well as they could and should. And so before we get into that though, we're going to go through some housekeeping slides. So if we can advance that first slide there. And then first thing we want to talk about is if you can't hear me right now, or if you're having any issues with GoToWebinar, I first recommend to just log out and log back in again. A lot of times that works pretty well, but if you do have any questions, you can call the technical support. We've got the phone number on the screen there. That's for GoToWebinar, not for us. If you do want a copy of today's presentation, at the end of the webinar, there's going to be a post-webinar survey, and you can check a box that will get you a PDF version of this presentation. And also, if you want to listen later on, or you want to share this with a colleague or whatever the case may be, we actually record all of these. We put them all on YouTube. This one should be up there within roughly about a week or so. So if you can check that out from there. Alrighty, and then for a lot of you folks, you like to watch, because if you do watch, you get the certificate of attendance. So if you do watch the whole webinar, you should be seeing the certificate of attendance in your inbox shortly after the presentation. So keep an eye out for that one as well. And then, you know, despite the fact that we didn't have an AHR Expo this year, we do want to toot our horn a little bit here. We were an AHR Innovation Awards winner for our angle mix. It's a really cool product where you've got the hot inlet and the mixed outlet right in line with one another. Just seems so simple of an idea to put them right in line with one another like that, but we're pretty proud of this guy, and we wanted to let you guys know about it. So if you haven't seen it yet, definitely check that guy out. And then just a reminder with hydronics, our most current issue is issue number 29. It's going to be on heat exchangers and hydronic and plumbing systems. But we've got hydronics journals on all the different topics of hydronics and plumbing, so check those out as well. And on the next slide here, we want to remind you that we actually have a digital version of hydronics. It's actually interactive, so it gives you all the same information of hydronics, but then it also links over to various and applicable YouTube videos and other sources of material and information that you can use to your advantage. So definitely take advantage of that at the hydronics.caleffi.com. And next month, we have another guest speaker. It is a gentleman by the name of Ed Morris. He's the technical manager at Altechnic in the UK. They are our branch, a Caleffi branch in the UK. Awesome guy, very funny. He's going to be talking about dirt and debris in hydronic systems and getting all that stuff out of there. So definitely tune in for that one. And without further ado, I'm going to introduce Mark. Mark's done a couple of these webinars for us now. This is his third. I think this counts him as a regular at this point. And he's got a great mind for diagnostics and troubleshooting. And I think his presentation style is fantastic as well. So definitely soak all this in. And thanks, Mark, for joining us again.
Well, you bet. And thank you, folks, for inviting me. Thanks to Caleffi and the team behind the scene that puts all of these great programs together. There's no shortage of a need for education. It's ongoing. I've been doing it for about 48 of my 49 years of being in this business, and I love sharing knowledge with everybody to keep them from making the same mistakes that I've made in my illustrious career. It basically saves you having to try to reinvent the wheel. So today, this is an extension of one that we had spoken about before with domestic hot water heating issues. And unfortunately, we seem to have become the experts in the Denver market. And by the way, thanks to my employer, Advanced Hydronics, Jim French and Tom Olds, for allowing me the time during our regular business hours to put these slide programs together and share. I'm responsible for education content within Advanced Hydronics in Denver. And if you happen to be on the market looking for a job, please give us a call. We're in dire need of good help. So today, let's move on here. What's wrong with my domestic hot water delivery system? Our experience with this is basically primarily focused on multifamily and the motel hotel markets, where you have large domestic hot water heating systems. A lot of these systems are up for renewal and have basically been worn out and have had issues over the years. And whenever one of our contractors or ourselves go out to work on these things, you're going to own that system when you get done. And it comes, generally speaking, with a lot of baggage. You're going to make changes that are going to cause additional changes in the operation of the system in the field itself, which, again, everything was fine until you came. And in the reality of the matter is, there were problems that were existing already. They just kind of glossed over them and said, yeah, that's the way it's always been. Mentioned to Cody and Max the other day, I had a job where we went out and saw a relief valve that was pouring probably about a gallon per minute into a floor drain off of a pretty good sized boiler, about a million BTU an hour boiler. And I said, how long has this been going on? And the guy says, well, I've been here for 3.5 years and Fred was here for 10 years before me. And he said, it's always done that. Isn't it supposed to? And people just take it for granted that that's the way that it's supposed to be. And the reality of the matter is, it is not. So today's topics, we're going to be reviewing the ideal domestic hot water supply and return system. These are rare beasts. I think I've seen one out in the field, and it's one that I actually ended up having to do some work on anyway. Troubleshooting of hot water delivering issues themselves within the buildings, and there is no shortage of issues in the field. Many of them are multiplied. They have situations where you've got more than one situation to deal with. So we'll be looking at the analysis of cross connections between hot and cold water lines, which are a very common occurrence from the field that will create all kinds of nightmares for you. Solutions with thermal balancing. These are things that we did not have for many years. And God bless Caleffi and their forward-thinking engineers that brought these products to the market has been a godsend in taking care of issues of, well, I don't seem to be able to get hot water in the far end of my building. So I called a plumber and he came in and put a bigger pump in. He said, if a little pump does a little good, then a bigger pump will do a lot of good. And shortly after he did that, we started spinning pinhole leaks in all of our domestic hot water circulation return lines. They don't make them like they used to, do they? Actually, they make them better than they used to. It's just a matter of looking at these problems and figuring out what the problem is and bringing the proper answers to the table and taking care of these issues. So we'll be also examining the domestic hot water supply and recirculation return balance during periods of non-use, overheated loops, overcoming thermal migration, and overheating the loops with digital mixing. And then we'll fall back and take a look at the quote unquote ideal domestic hot water supply and recirculation return system that you will hopefully run into in the field. So let's jump right into it with some slides here. I'm going to be using my cursor to show you certain points within the system itself. And this is the ideal domestic hot water supply and return system. Now, down here is typically where your boiler will be. And people that are familiar with the indirect domestic hot water heating systems on the market are very used to using a large storage tank with a small heat exchange surface in the bottom of the inside of that storage tank itself that requires an extremely high approach water temperature, typically around 180 degrees, in order to kick a storage tank temperature of 140 degrees. And that is pretty much been the standard for our industry since I've been at it for the 49 years that I've been doing this, but things have changed. We now have reverse indirects. With a reverse indirect domestic hot water heating system and the application of a high efficiency modulating condensing heat source, you actually only need a boiler supply water temperature that's about 10 degrees hotter than your desired storage tank temperature. So if I wanted to maintain 140 degree Fahrenheit temperatures within my storage tank itself, I'd only need a supply water temperature from the boiler of around 150 degrees for this to work, which means that if I've got a 10 or even a 20 degree delta T on that system, basically I'm going to be seeing that modulating condensing boiler at its peak efficiency with a return water temperature of around 140 degrees, even while it's doing domestic hot water production. If you do have a small coil that does require 180 degrees Fahrenheit, your appliance is going to leave its high efficiency condensing mode, but the good news is that it's only usually for a very short period of time. But if you are using the reverse indirect storage tanks types of system with these modulating condensing boilers, you can achieve condensing temperatures even while you're doing domestic hot water production. So again, following our source here, we want to maintain the storage tank at temperatures above 140 degrees. And that's basically to alleviate the potential for the growth of bacterial, waterborne bacterial, including Legionella, which is the most commonly misdiagnosed disease in the world. Even at 140 degrees, the bacteria can survive, but its longevity is significantly less at 140 than it would be at temperatures of less than that. So by maintaining a storage tank of 140 degrees Fahrenheit, we need a mixing valve. And this mixing valve is essentially going to lower the discharge water temperature from our storage tank to the load itself. And typically we'd like to see a distribution system supply water temperature not in excess of 130 degrees. Unfortunately, we have a lot of lawyers here in the United States. Some of them specialize in scald water type situations. And if you want to alleviate yourself of any liability, then you've got to maintain discharge temperatures that are going to lessen the potential for scald occurring. Scalding can occur at 130 degrees, but it's significantly less than the water temperatures at 140 degrees. The time-based factor is significantly longer at a lower temperature. Common sense needs to be applied wherever possible. But in any case, this mixing valve is a critical situation if you've got a storage tank that's being maintained at a temperature above 140 degrees Fahrenheit. So on draw, basically the hot water is mixed with the cold water, and then you get this discharge temperature going out. This is an ASSE 1017 point of generation mixing valve typically, and not all of them are 100% close off on the hot port. And I will show you the consequences of that as we go further into this slide. So the distribution system, basically, this is like a large hydronic heating system. This is the energy source itself. This is a distribution supply main that goes out. We have risers that go up. Tried to keep this as simple as possible. I've had as many as 14 stories worth of buildings and didn't want to clutter up the drawing. So I've eliminated boilers, certain isolation valves around the mechanical equipment within the mechanical room itself, and basically wanting to focus and concentrate on the distribution system of the hot water supply, as well as the circulation return. The circulation return begins basically at the ends of the hot water supply, and that circulation return is then brought back down to the energy source itself through a constant speed circulator and a functional spring check valve. And I know that a lot of people say, well, why a spring check versus a swing check? If the pump is in a continuous run mode type situation, that swing check is going to be in the open position, and it will lime itself in the open position. And consequently, you won't have the ability to be able to stop any potential backflow occurring within the circulation return system. And I've had people say, well, if the pump's running continuously, there shouldn't be any circulation going backwards through there, should there? I would agree. You would think in your mind's eye that that wouldn't be the potential, but the reality of the matter is that water pressure and flow are going to follow the path of least resistance. And I have seen situations where even with the pump running, if it's a low head pump, you can force that pump to basically allow water to go flowing through it backwards to that distribution system. So our cold water comes in here on draw. Basically, you've got cold water coming into the bottom of the storage tank, which forces the hot water out. The hot water is mixed with the cold water at the mixing valve, and then you get the tempered water that's going out through the distribution system itself. During periods of non-use or non-draw, then essentially this circulator is the only item that's moving water through that system. And if you've got a good 1017 valve, as this water gets too hot, then basically it's going to close this hot port and blend this cooler return water coming back out here with the hotter supply water coming from the storage tank to maintain this discharge temperature. But again, not every 1017 valve is 100% shut off, so we'll look at that as a potential issue going forward. All right, so the most common situation that I run into in a lot of these apartment complexes is basically a failed shower valve, a cartridge style of shower valve. One particular brand that I'm very familiar with, and the company is the only company that I'm aware of that has actually admitted that they did have an issue at one point in time, is Moen. Moen had the single lever cartridge valves, which would lose an O-ring someplace within that cartridge assembly itself, and would essentially create a condition where you could get a cross connection between the hot and the cold water line right across this valve right here. So basically what's happening is water is following the path of least resistance. So on draw, you normally would have this pre-mixed hot water that would be coming up here and would be taking care of the call for hot water demand anywhere within this riser itself. But if this valve is cross-connected, then basically you've got cold water shooting straight across that valve body, mixing with the hot water coming from the source and diluting the water temperatures that basically are rising up through that riser itself. So it creates a condition where basically anywhere above this point, they get extremely lukewarm water. They just can't get hot enough water to be able to shower in. As a matter of fact, the average water shower temperature is between 115 degrees and 117 degrees Fahrenheit. And I used to work with a company that was in the business of manufacturing low flow shower heads that actually did a study, and this is the information that they came up with. So everybody always wants to know, what is the water temperature that people use? Well, you can have it coming out of the faucet at 130, but they're going to mix it down to their personal use, and that's typically around 115 degrees Fahrenheit. All right, so how the heck are you going to find this? And bear in mind, this is really important that you listen to not only the customer, which is going to be the management company that is running the facility, but also to the residents. And in my 49 years worth of experience, they've both lied to me. I mean, you have some residents that have a problem with management and they just want to prove them wrong regardless of what they have to do. And they will lie to you. But typically, management doesn't want to accept the fact that they've got problems within their systems, so they'll lie to you. They say, yeah, no, there's no problems. You know, there's a few people that complain, but they always complain. And I have found that when you talk to the residents and just be honest with them and say, hey, you know, have you had any issues with hot water availability? Is it always available? Is it too hot? Is it not hot enough? Are there certain times when it's not hot enough? Then they'll give you the truth. And they're the people that are the end users that really are there in the field dealing with this, as opposed to the maintenance man that looks at the water here and says, it's set for 140 degrees. I can't make it any hotter than that. And they don't look at these as a distribution system issue. So, and speaking to the residents and management, anytime before you go into one of these buildings to change the system, ask the residents as you're doing a tour through their facilities, ask them questions and bear those notes in mind, because if you don't, it's going to come back to bite you. You will notice in this particular installation that we're using what we call a reverse indirect, and this is that super efficient storage tank system. Bounce back here real quick to the previous slide versus a conventional indirect. And on a conventional indirect, you've got basically a large storage tank with minimal pressure drop going through it on draw, whereas with the reverse indirect system, you're going to have a situation where you've got a pretty significant amount of pressure drop occurring within this system. And quite honestly, this cross-connected valve has probably been here for many years, but it's been masked by the fact that the pressure drop through the domestic hot water storage tank has been minimal, so it's never really raised its ugly head. Now that you've changed to this new high efficiency reverse indirect, you've changed the dynamics on the system, and all of a sudden problems start cropping up. Well, it worked fine before you guys got here. Nobody's ever said that to you before, have they? I hear that daily. All right, so what are we going to do to be able to find this? Number one, you've got to have a questionnaire that management takes into consideration that tells them exactly where these shortages are. If you've got a 14-story building, it could be anywhere between the first floor and the 14th floor of the building, and you need to fine-tune that area of focus. And once you do, then you can go in and start saying, okay, well, let's take a look at this and see what's going on. Typically, there is one supply in return for both the hot and the cold that is supplied through the showers, with branches that come off and take care of the lavatory that's in the same bathroom. So if you go into the bathroom on the second floor of this building, where this notes have been coming back saying there was a shortage of hot water above that point, and you try to get hot water from that lavatory, if you can't get hot water from the lavatory, hey, you're pretty close to where that cross connection is. And typically code requires isolation shutoff valves for all of these shower valves within the system itself. So if you can use the screwdriver stop and shut off the cold water supply to that shower valve, and all of a sudden you've got hot water at that lavatory, bingo, you just found the problem. You just found the first problem. There are probably multiple problems within the system itself, but basically you've just found one of the problems that definitely needs to be taken care of first. So the simple thing to do would be to replace that failed shower cartridge valve with a new one, and then start the system back up and check it and see if the problem's up above that one away. But bear in mind that you could have numerous failed cartridge valves within any given facility. I think I counted at one point in time, we had 14 failed shower valve cartridges in one building that we had to find and fix before we could get to the other problems that we'll discuss coming into the systems. All right, so let's keep moving on. Another issue that we have found has been cross connections that were unintentional but were man-made. If you will note here on the second story, at this left-hand side here, I put a little bitty ball valve downstream of the actual shower mixing valve itself. There are these remote wand type of shower heads that have a shutoff at the actual shower head itself. And what we found was a lot of residents had to wait so long for the hot water to get to their apartment that they would go ahead and turn that on. Well, that shutoff valve does not shut off 100%, so it keeps a continuous trickle of hot water coming to that point of use. And it's great from the standpoint of being able to hop in and get a quick hot shower, but from the standpoint of wasted water and energy, it's very, very bad. And this cross connection can occur not only at the shower valve, but it can also occur at a kitchen sink. There's a portable laundry machine that you can get from Hoover that basically has an adapter that you put onto your kitchen sink faucet. And if you want warm water, then you set the faucet for halfway between hot and cold, or open up both the hot and cold water tap. And then there's a solenoid downstream at the actual washing machine itself that will basically cycle off and on to fill the water within the washing machine itself. Well, that's essentially the same type of cross connection that you've got that's occurring with the shower valve, except that it's actually occurring at the kitchen sink faucet itself. Or another scenario has been where they've got a mop sink. If they've got a mop sink where they have a hot and cold water line that comes into it with one common spigot coming out, and they have a shutoff valve downstream of that spigot, then basically the same thing. They create a cross connect where the hot and the cold water are basically cross charging. If you've got check valves at the cold and hot water supply to these systems, then this is a non-issue. But in some of these older buildings, check valves are not a requirement at that point in time. I know that there are certain jurisdictions that do require check valves on both the hot and the cold water supply going to their shower valves. So that would eliminate this type of a problem. But in most older buildings, check valves are not a requirement. So basically the thing that you have to do is after you've found the cross-connected cartridges, now you need to go through and find any of these situations where the residents are using that remote shutoff valve, or it has a washing machine within their apartment, or a slop sink where the hot and cold water line were left on and the downstream valve was closed, so that you essentially created your own human cross connection between those two. So that's one thing to watch for. And again, if there's an integral check valve in the shower valves, then it would have stopped this type of a cross connection. So on the newer buildings, this is less of a potential, but on the older buildings, it's definitely a potential. All right, so the next slide that I'm going to show here, there we go, is basically a situation that is quite common. And I've mentioned this before. I always recommend the use of a spring check. And I've seen spring checks foul as well, but the potential for a spring check to foul are significantly less than a swing check. A swing check can only be used typically in a horizontal flow type situation or a vertical upflow situation, but never in a vertical downflow situation. That's been an industry standard ever since I've been in this business. Some people don't realize that. And the cost of a swing check is significantly less than that of a spring check. So it's not uncommon for people to go, well, a check valve's a check valve, I'll just put this in. And the reality of the matter is that there are limitations where you can use it. And I've had less failures with the spring checks than I have the swing checks. But essentially what's going to happen in this situation is we've got the cold water supply coming into the domestic hot water heating system, which is going to drive the cold in and the hot out, which then hits the mixing valve, mixes the hot with the cold, and gives you the tempered water going back up to the system itself. But basically, due to the fact that this spring check or the swing check on the circulation return is not working correctly, you've essentially got cold water that's charging backwards through the circulation return, going all the way over here, and it's mixing with the hot water, so that the hot water that comes out at this furthest point of use, which is typically the top floor, is going to do a couple of things. First off, you get a cold water sandwich. It starts out hot, and then all of a sudden when the cold starts working its way back through the circulation return, it goes cold. And then the pressure drop increases on the circ return, so the water starts flowing back through the hot water supply again, so it comes hot again. And that's what I call a roller coaster ride of temperature change. You're continuously changing the valve, trying to get a common comfortable temperature. And the reality of the matter is that the flow is basically changing right at this point here. Some of it's coming from the supply, some of it's coming from the return, and it keeps changing. So the easy way to find that is to feel right here on the circulation return during peak demand. If this is cold, you've got cold water that's basically charging backwards through that circulation return and making it all the way up to the top of the circulation return system itself and diluting the water at that point. And it can occur in numerous risers. It doesn't have to be in just one, but it's typically the furthest point away from the source of hot water itself, and also the extension of the circulation return coming back in here. So feeling right here where the circulation return comes back in, this should normally be warm, even during a draw period. If this goes cold during a peak draw period, then essentially you've got cold water that's working its way backwards through this whole system.
Mark, we had a quick question here too, and I think it's good to bring it up. You've got this picture here with the reverse indirect. You mentioned by changing the system, you can create problems that you might have been masked before and things like that. With a a standard indirect, you've got very little pressure drop. With a reverse indirect, you've got much more pressure drop, which can cause these issues. Will you see the same issues with tankless type water heaters and banks of tankless as well? I mean, it's a similar idea, right?
Yes, you will.
Yep.
Anytime you change the dynamics of the system, which in this particular case is the pressure drop, then yeah, you basically set up a whole new set of operating rules that the system's going to have to comply to. And anytime you create more of a pressure drop on the system, it's going to change the dynamics within the system itself, and problems that were being masked before all of a sudden won't be masked. They will be unmasked and they will become your problem. It worked fine before you worked on it.
Yep.
So yeah, and this is a reason that I like to ask these questions as we do our initial surveys. We do a lot of work for the state of Colorado, Department of Energy Outreach Colorado. And if I'm involved on a project and I'm going through, I like to ask the residents these kind of questions, because if you ask management, they're going to say, no, not really, there's no issues. And then all of a sudden there are issues, and they're your issues. You've got to take care of them. You touched it last, you own it.
Yep.
And if you're aware of them going in, then you can make management aware of them and say, hey, look, I realize that you guys are doing a really good job of maintaining these systems as well as you can, but there are issues within this system that when we're done, we'll probably raise our heads. So just be prepared. We'll work with you in finding these. We provide them with the necessary forms that their office managers can answer the questions and kind of narrow it down to an area. But yeah, absolutely. Anytime you change the pressure drop on the system, you're going to find all kinds of new problems that weren't an issue before.
Yeah, and I think too, another thing you mentioned too, it's a great thing to bring up is understanding your customers' expectations and making them aware of some of the expectations that they should have too. I mean, the fact is that you're working on these systems, they're spending a lot of money. If something bad happens down the road and they're not expecting it, then it's all your fault. And if you kind of prepare them, I think that's going to go a long ways. So.
It does. They appreciate you. Most of the other people that come in there aren't asking any of these questions, and you present yourself as a professional and you're prepared. And not only do you realize that there are going to be problems, but you also bring solutions to the table.
Yep.
So here's a prime example. If we had installed the Caleffi Series 116s with check valves at the tops of all these circulation return lines, the circulation return would not have been allowed to run backwards, even if its check valve would have been fouled. So this is a situation where you address not only the issue of cold water sandwiches and roller coaster ride temperatures at the top of the system, but by having this device installed in here, essentially you set up a scenario where everything's going to be thermally balanced. All of the complaints go away. The residents love management. Management loves their maintenance team, and everything works out great. But one thing that's always missing on these systems is this Caleffi quick setter. We put a quick setter on every system that we install the Caleffi Series 116 valves into. And you do this for a couple of reasons. Number one, it's great to be able to see and verify that you've actually got flow coming from whatever circulator you have. But it's also important to limit the velocity of the water below that of erosive velocities. And with domestic hot water heating systems, I typically like to target around 3 foot per second. Right. So if I've got a 1 inch combined circulation return coming back, and I look at the flow charts for that, that's going to tell me how many GPM I should limit that to. And this kind of throws us into some other areas of like, well, how big does this pump need to be? Well, that pump only needs to be big enough to basically guarantee that you've got at least a 0.5 gallon per minute circulation occurring at the very top of the system. which is where your circulation return would begin, but it's also limited by the size of the pipe that is basically on your circulation return down here at the bottom of the system, that you're going to be using the quick setter to basically limit that flow at that point. And you set this flow setter with the system cold, because the system gets hot, then the Caleffi Series 116 valves are going to start kicking in and choking flow down based on their temperature of water coming back to them. So that's not a true worst case scenario situation. So after you've gone through and you've installed all of these valves and you installed the flow setter and you've got a cold storage tank and you are purging the hot water out through this whole system, including the circulation returns coming back in again, do it with cold water first. And if you do it with cold water, then essentially you're going to be able to see what the maximum worst case scenario flow rate is going to be on that system. And it's essentially going to allow you the ability to limit that flow and end up with minimum required flow rates necessary to be able to get the system to work correctly. For some reason, my picture forwarded itself without me asking it to. Thank you. Back to this picture here again. Essentially, the problem would have been indicated by the mixed water temperature at the furthest point of use, which is typically the top floor, assuming that the physical plant is on the bottom floor. If your physical plant is on the top floor, then this scenario would possibly be a situation where the mixing was occurring at the bottom of the system. So you've got to look at these systems as a whole. And unfortunately, the plans are not available for these systems, especially the as-builts. They may have the as-designed, which are still very, very handy, but as it pertains to the as-builts, it's never done. These systems are typically piped parallel direct return, trying to reduce the cost of the installation itself and keep it simple for the actual installers themselves. And with it being parallel direct return, basically the water is going to have a tendency to follow the path of least resistance. Whereas once you put these Caleffi Series 116 valves in here, then basically they're going to balance the system out and the problem's going to go away. All right, so here's another scenario that I've run into before. Basically, this is a situation where the valve, the gate valve, and gate valves, unfortunately, have been used quite extensively through most of the hot water heating systems that are out there. And typically, these gate valves are on the bottom of all of these risers that are going up on both the hot and the cold water line. Well, these gate valves are very susceptible to failure. Unfortunately, they don't get exercised on a regular basis. And the first time it's necessary, as an example, well, Fred, our new maintenance man, went up to the third floor and took the screws off the face of the valve and blew the cartridge out of the valve. And now we've got water running wild in the shower. We need to shut the water off. Emergency, emergency. So they find these valves. I remember seeing these valves on the ceiling and they close them off in a hurry. They don't go in part way and then back out and kind of, renew the slides and the threads and the guides and make sure that they can get that gate all the way in and get it back out again. So consequently, they slam that thing shut. And when they get ready to open it back up again, it strips all the threads off of the stem, and voila, you got a valve in the closed position with a handle that spins free. That to the maintenance man, he thinks, well, yeah, I opened it counterclockwise to open, right? Well, the gate is dropped in the bottom of the valve, and it consequently is not working in the standpoint of being able to be opened and allow any flow through the actual system itself. So basically what we're going to have to do is to find that broken valve and replace it with a ball valve. But quite honestly, a ball valve, if it's not exercised on a regular basis, will also fail. So it's a good idea to talk to maintenance about the possibility of instituting an annual valve exercise program. And it's not that hard. They go in there during periods of non-use, which are typically after 8 o'clock in the morning, before noon, and just basically close it and open it. And then the next time they need it, it's functional and they'll be able to take care of it. But what will happen under the scenario with this valve basically being closed, essentially what's happening is the hot water for this riser is being supplied off of the top of the circulation return line. Come on, back here. Nope. Pardon me while I take me back. So the hot water would basically be charging from the circulation return back down through this riser, because remember, this valve down here at the bottom is in the closed failed position. Pressure is basically going to flow from high to low. So instead of basically having the hot water supply being run through here, it comes up here and it charges back down this riser. and that's where it's getting it from. And I had a hotel out in California where they had a failed valve, and they were basically supplying a whole wing of domestic hot water through the circulation return. And they kept springing pinhole leaks on these circulation returns. And they said, yeah, they don't make them like they used to. No, they don't. They make them better than they used to. This is an erosive velocity situation. Once we figured out where the valve was that had failed, went in and did a real quick emergency replacement, pulled the guts out of the valve, and restored the supply water temperature going through it again. They'd been fighting this problem for 20 years. They put in flow restrictors, they put in low flow shower heads, they put in bigger circulation return pumps. They did everything, but they could not find where the problem was coming from, and it was essentially a failed valve. So replace that valve if you possibly can with a good ball valve, and essentially eliminate the possibility of running back into this problem again. It's not always possible to be able to do that, but whenever possible, do it. Use a ball valve, much more dependable, much more reliable. All right, here we go into another scenario here that everybody is familiar with. In fact, we were talking right before the seminar started that one of the most popular after the fact videos that have been watched on the Caleffi website was one on domestic hot water and high temperature situations occurring within these distribution systems themselves. Excuse me. The ASSC 1017 does not require that the hot water port for this valve be closed completely off. So during periods of non-use, essentially all you have that's moving hot water through the system is a circulation return pump. So if this hot water port is not closing completely off, whatever storage tank temperature you have within the system itself is eventually going to work its way throughout the whole system, including through the circulation return and back over here again. And 140 degree Fahrenheit water in a domestic hot water heating system is a dangerous situation. I don't think I'll find anybody that will argue with me about that. There are lawyers that make a living off of chasing hot water scald type situations, and this is not a normal consideration. Once the draw begins at the point of use, then the mixing valve kicks in and it does exactly what it's supposed to do, which is to mix the hot with the cold and give you a blended water temperature going back out to the system itself. But during periods of non-use is when you get into a situation where thermal creep is one term that I've heard called, I call it hot water migration. Basically, whatever is in the storage tank is going to work its way out through the distribution system and all the way out. And the simple, quick, easy fix for this whole situation is to go to a 100% bubble tight close off valve like the Caleffi Legio Mix. Come on, I can see you. There you are. The Legio Mix is basically a ball valve. It's a three-way ball valve with a very sophisticated controller and motor operator on it that basically is extremely accurate, and it's not going to allow that thermal migration to occur. So essentially what happens is if the distribution loop temperature downstream of the mix valve itself is too cool, then it's going to close the cold port and open the hot port, and that circulation return is going to push that cooler water through the heat exchanger, push hotter water out, but it will also find itself in a situation where it's partially hot and partially closed, open, and basically mix that water temperature that's going out to the actual load itself. So even during periods of non-use, you won't find yourself in a situation where you've got 140 degree discharge temperatures that are working its way through the loop. And it's also got a feature that I wasn't aware of that Cody was telling me about the other day that has the ability to be able to do data logging, which is important. That's one of the tools that you're going to need. If you're going to find yourself going out and doing troubleshooting on these systems, you need a couple of different data loggers, preferably a 4-channel per data logger. I like a company called Hobo. I'm trying to remember the name of the company. It's Onset Computers. Makes a relatively inexpensive and quite honestly, there's a plethora of data loggers that are available out there that you can use, but you've got to have this because you cannot stand there 24 hours a day, 7 days a week trying to watch the system under load, non-load conditions. And the Legio Mix actually has the ability to be able to log these temperatures, and you can see exactly what's going on. So if they say, yeah, we're running out of hot water, you can look at the Legio Mix and say, well, you may be running out of hot water in your distribution system, but it's not from the source of supply. We're showing this constant availability of 130, 120, 128, whatever you need.
Yeah, Mark,
So
we
it's,
actually, it was a really interesting story. A lead mix was installed in a large chain hotel not too far from our offices in Milwaukee, and they were having issues where, like, every day they were having issues with it, what they thought was the mixing valve. And again, due to that data logging, they were able to go in there and see the average hourly temperatures, and they could see from like this hour in the day in the afternoon to this hour in the afternoon, all of a sudden like the recirc temperatures were coming back all strange, and the mixing valve was hunting more and everything else. And what they ended up tracking it down to was one of the maintenance people was putting on a Y hose onto a mop sink, filling up mop buckets, but they'd have a shutoff downstream of the shutoffs for hot and cold, and creating that cross connection like you talked about before. And by using that
mhm.
data, they were able to say definitively it's not the mixing valve. The mixing valve literally works 23 hours of the day or 22 hours of the day. It's just these 2 hours, what's happening during these 2 hours. And it was really very useful. And yeah, I mean, use it to your advantage. Data is definitely helpful.
It is. And if you're going to be doing any troubleshooting and sleuthing on these systems, you need data loggers not only at the source of supply, but also at the top of the system or the furthest point away from the system, so that you can get a true picture of what it is that's going on. And once you can see what it is that's going on, then you'll know what areas to go look at from the standpoint of, where is it coming from? Is it a cross-connected shower valve? Is it a cross-connected lavatory faucet? Is it a mixing valve that somebody put downstream of their bucket filler? Or is it in the kitchen from a pre-rinse spray? I mean, I see all these scenarios, and I've had situations where all of them were within the building itself. I had failed check valves. I had failed cross-connected shower valves. I had people using automatic washing machines in their apartments that were leaving the hot and cold water lines open. But you can only basically address those issues that you can see. But if you can't see them, you can't address them. And if you've got data loggers that are sitting there watching the system, then you can basically see what it is that's going on and say, oh yeah, here you go. Oh, well, heck, you're running out of hot water. What's going on with your boiler? Oh, well, it's stuck on low burn. I mean, there's a whole lot of different things that you can use, but it makes you look like a professional. And the next time these people have a question, they're going to come to you as a source, because they know that you're going to go, well, I don't know what it is. Let's try to change this and see what happens. Oh, it didn't work. Well, let's put in a bigger pump and see what happens. Well, you started spraying leaks. Well, you probably need to do pipes anyway. So it's
Like,
it's a good tool. Another
I
good
was gonna
tool is an infrared camera.
Yeah, for sure. I was going to say too, Mark, after working with you on this one, I was at home at my kitchen sink, and a lot of people nowadays have these faucets where you either can just touch the faucet and it'll turn on, or you wave your hand over it and all that other fun stuff. And I remember when I installed it, it actually came with check valves to put at the stops. They were a little male by female check valve. Obviously, if you've got the cartridge open all the time, it's set between hot and cold, or in my case, we just put it on hot all the time because we're always rinsing dishes. But it's going to create a crossover like that. And I just remember distinctly in the manual, it tells you to put these check valves in, but they don't tell you why. They don't give you a reason for it. And I could just imagine a lot of people just throwing those off and saying, what do I need those for? So.
Yeah, I think Massachusetts state plumbing requires check valves on everything. Anywhere that you've got a hot and cold water line connected to a shower valve, lavatory, whatever it happens to be, they require the check valve. So kudos to them. It becomes, it eliminates a lot of potential problems. I'm really not sure why they require check valves. I suspect it has something to do with their question about the potability of hot water, which hasn't really changed. If anything, you've reduced the bacteria count by heating the water than you would from not having heated water. But regardless of what the reason is, it's an excellent situation. So those people that have those check valves are going to be less susceptible to cross-connected failed shower cartridges, or people using automatic washing machines in their apartments, or leaving a shower head shut off at the wand and leaving the mixing valve preset to a preset temperature. And as you said, your new solid state electronic valves, I never thought I'd be replacing batteries in my valves at the same time I'm replacing the batteries in my smoke detectors, but here we are. Who'd have thought?
You're correct. Yeah.
Now, come on, computer, move forward. All right, here we are to the question section. And one of the things that I did mention before was the use of an infrared camera. Infrared camera, I've got one that I paid $5,000 for. And at that point in time, that was a pretty good deal. I've had this camera for about 10 years now. They've gotten them down now to the point where I think they're like $300 an attachment for an iPhone, and they are fantastic. You can see heat in the form of color, and it's extremely impressive to the consumer as they're standing there watching you doing this analysis going, oh yeah, look, you know, the cold is shooting straight across that shower valve into the hot. I can see it. You'll have to take the chromoscutcheon off the face of the actual valve itself. That's not that hard to do, so that you can see the oxidized brass valve body. Otherwise, the emissivity is going to mess with you. But you can see this stuff occurring, and it's like, oh wow, that's impressive. Yeah, well, we just found one cross connection. There's probably others, but let's eliminate this one, replace the cartridge, reset the system, let it run and see what happens. The problem is going to migrate. If there are still other issues within that system, then it's going to take you to another floor. And that's where it's important for the customer to log every complaint coming in. What unit number, what time, what was the nature of the fluctuation? Was it no hot water at all, or was it variable? Was it lukewarm? Was it ice cold? And that's basically going to give you the information that you need to put powder into your bullet so that you can go out there and kill that problem. And having this instrumentation, the data loggers at the legiomics, the data loggers on the system as a whole, watch the boiler supply and return line, make sure that it's not a source of supply issue. Then basically it sets it up so that you can see exactly what's going on, you can see where the problems are, and basically come back to them and say, okay, here's what we found, here's what you need to do, here's what we need to do. And once you do all of this, we're seeing reductions of water and energy consumption of between 20 and 30% on these systems. People are not wasting water waiting for hot water to get there. The distribution system temperatures themselves are going to change. Let me go back to a system here, the ultimate ideal system. Basically, if you look at what's going on here, we're still maintaining 140°F water temperatures coming out of our heat source itself, and that water is being sent through the system post-mix. And up to this point, when we've got our collecting 116 series valves in here, the thermal balancing valves, essentially the temperature of the distribution system all the way back down to the actual heat source itself is significantly reduced, right? So our standby losses from that circulation return system are going to be minimal at best. Basically, we've gone to a DC ECM type of constant pressure circulator that once these valves start closing, it's going to see that, it's going to reduce its parasitic cost of operation. So there's all kinds of benefits to applying these products in the field. The legiomex is going to give you data logging capabilities so that you can see exactly what it is that's going on with the supply and return system. The Series 116s are going to basically balance this whole system out. I've done this as parallel reverse return. That's a rare animal in the field. It's usually it has been done in either a parallel direct return or a parallel parametric return, neither of which are simple or easy to balance. But when you put these balancing thermal balance valves in here, they will take care of themselves. The problems will go away. The discharge temperature from the circulation return line is going to be reduced to a minimum of around 120 degrees. That's typically what we set our little Caleffi setters for. So you're guaranteed that these people have always got 120°F water for this point of use. Now, what doesn't show here, and is a potential that we can do with the Series 116, is to put a powered bypass around that thermal balance valve itself so that you can go through a nighttime scald sanitization on the system. That's a standard in Europe. You don't do this in the United States because we don't require mixing valves at every point of use. And typically the Europeans do this when there's nobody up using any hot water, like between midnight and 2 a.m. Well, if there is somebody that is up using hot water at 2 a.m., which you know that's going to happen, you want to make sure that you've got them protected. So the only way that we would be able to do this would be if the contractor were responsible for the system design from word go. And he would incorporate mixing valves at every point of use, lavatories, kitchen sinks, the anti-scald features on the shower valves themselves. Then you can send the system into a thermal scald at night and kill any bacteria that's in the domestic hot water heating system. I've had these conversations with numerous code authorities, and they agree it's a really good idea, but they have other issues that they need to address first. I think we will eventually see ourselves doing this, but there are so many changes that are going on with our energy codes at this point in time right now, it's hard to keep up with them. I got notification the other day that they wanted to put in basically the equivalent of a proximity sensor or an occupancy sensor in every bathroom, so that when you walk in there, it notices that you're there and it turns a valve open and starts a pump to circulate hot water through the system, so that when you get ready to wash your hands, that it's readily available. All of these things sound like a really good idea, but it's going to add cost to the systems, and there are existing systems that we have available, including the scenario that we're showing here, that are going to reduce the installed cost of the system, provide plenty of hot water to the point of use, minimize waste on the system as a whole, and make the system as efficient as it possibly can be. So that's the ideal ultimate, I guess I should call it the American ultimate ideal domestic hot water supply and return system. Basically a good anti-scald valve, a good heat source, a good thermal balancing system within the system itself, and set it up so that all of the complaints go away. The wasted water and sewerage and energy associated with that are also going to reduce, and there's benefit to it. I mean, you could probably show a return on the investment. I've never really bothered to do that, because just making the phone stop ringing in the maintenance office was more than enough. I hope we got some questions.
Oh, we do, Mark. We do. This was fantastic. I mean, talking about just the different scenarios of what you've run into and how to correct them, and taking steps further than just I need to put in a bigger circulator, or I need to turn up the water heater, or whatever. I mean, I think it just makes all the sense in the world. One thought that came to my mind, we talked about recirc creep or temperature creep, or thermal migration, I think you referred to it as, on one of the slides. And I've seen it in a lot of diagrams from various mixing valve manufacturers, where they, in some cases, recommend it. Sometimes they even require it to have an aquastat on the recirc return, to basically shut it off if it gets up to temperature. But what are your thoughts on aquastats and timers and things like that on those kind of situations?
It's a stopgap. That's usually the first thing that they do, and saying, hey, what's causing this over temp condition? Well, it's that pump. Okay, well, let's turn the pump off. When the water comes back here hot enough, let's turn it off there. Okay, so the water gets back to the pump at 120 degrees. If you've got a 20-degree delta T between there and the furthest point of use, you still got 140-degree Fahrenheit water making it to the points of use. So it doesn't really address it. It limits it, and it may negate some of the complaints, but it doesn't really address it. You need to address it at the point of generation, as well as the circulation return through thermal balancing and a properly sized pump, a proper application of a pump itself. Don't use any of the old style constant speed. I don't care what's going on. I'm going to chew up the same wattage, whether I'm doing a deadhead or if I'm moving my maximum GPM, and set that system up to be as efficient as possible. Some of the other scenarios that we see is some manufacturers that basically show two different circulation return paths, one coming into the bottom of the storage tank to push hot water out, and the other one coming back up to the mixing valve itself. Well, if you've got a good working mixing valve, you shouldn't have to do that. And in my experience, it's kind of like having a fixed mix injection on a hydronic radiant floor heating system. The only time that it's going to be correct is if you're there at design condition. And the chances of you being there at design condition to set this up are slim to none. So you set it up based on whatever information you've got available to you at that point in time. When December 21st shows up and it's extremely cold outside, your phone starts ringing, and they go, you know what, it's not warm enough in the house here. And you go out and look at it and go, yeah, I need to tweak this a little bit more and make this adjustment and try to get it as close as I can. Well, you've got too many variables. And as long as you've got variables, it's only going to be right. It's like a stopped clock. It's only right twice a day. And having a good ASC 1017 bubble tight shutoff valve is basically going to eliminate the need for trying to do any kind of thermal balancing. The system's going to take care of itself. So yeah,
go ahead.
Go ahead.
I was going to elaborate on that too, Mark. The fact is that, you talked a little bit about Legionella and stuff like that. Legionella thrives not only in warm water between that 70 and 120 degrees, but it thrives in stagnant water. So anytime you're shutting off your recirc, you're allowing that bacteria to, have a little party, so to speak. You want to keep that water moving. And the other thing you're going to run into is every mixing valve under the sun, I don't care if it's small enough to fit in your hand, the palm of your hand, or if it's as big as a watermelon, every mixing valve under the sun has a minimum flow requirement. And if that recirc's not running, the recirc basically can handle the minimum flow requirements, and whatever draw you have past that is all fine and good. But if you have a mixing valve that has a minimum flow requirement of 8 gallons per minute, and you turn off that recirc, you know, that one person turns on a single faucet, that mixing valve is going to start hunting back and forth because it's not meeting minimum flow requirements, and it's not going to give you stable outlet temperatures, which can be a little bit of an issue.
Oh, it is. It is. And these problems are not unique only to these multifamily dwellings and motel hotels. Some of the houses that we work on are as large as some of these commercial properties.
Yep.
You know, that was some of the questions that came in the pre-question survey. I've got a large house. Should I do multiple pumps, or should I do one pump with thermal balancing throughout? And that would be my recommendation. One pump, keep your parasitic cost of operation to a minimum, and then put the thermal balancing valves at the furthest points of use. But it's also a matter of design. Take into consideration how that system's laid out. You know, make sure that you have hot water readily available within 10 seconds of demand. You know, and that's not that hard to do, but people don't think like this. I mean, another common sense thing that I'd propose to the codes was to have at least one joist bay of separation between the hot water supply and the circulation return, which would be in one bay, and your cold water line, which should be at least 2 bays away from that, so that you don't get into that thermal migration system problem where they go, I can't get a drink of cold water out of my house. Why is that? Well, you've got your hot, your cold, and your circulation return in the same joist bay. And even if they're insulated, the thermal migration is going to happen. You can slow the flow of heat, but you can't stop it. So if you've got 130°F water in the hot water line and 120 in the circulation return, the cold water line is going to see that and go, yeah, I want to be the same temperature. And it will be. And so it's just common sense. Separate those lines. Push them further away from each other. Is it going to cost you any more money? Not really. It's not that hard to do that right. And you're not paying for it anyway, the consumer is. And it becomes a sales advantage to you to go to the consumer and go, we're going to design your system, your domestic hot water system, and your radiant floor heating system using known technology, and make this thing as efficiently as we possibly can. And oh, by the way, you'll still be able to get a drink of cold water if you want it.
Yeah, no, it's very interesting. We had another question in here too, and you can probably pop back to that last slide where you had the ideal system there. They asked about, can you explain how the balancing valves and the ECM pump work together? Can you kind of just go over that as far as how those valves work and how that pump is doing its thing too, and kind of explain that a little bit more?
Sure. The ECM pumps are basically trained at the factory. They're taught what their capabilities are. They have a number of different settings that you can set them for. You can have constant flow. You can have constant pressure differential. And in this case, we recommend using them for a constant pressure differential. And this kind of also falls back to another question too that was asked about, how do I size that circulation return pump? Well, it's number one, there is no quote unquote load. You know, whereas with like a heat emission system, you've got 500 BTUs per linear foot for baseboard. And so you can calculate how many BTUs per hour you're going to have. You know what your flow rate is, you know what your supply water temperature is, and the delta T is what the load, quote unquote, is going to be. Well, the only load on this system is basically the standby losses of the piping distribution system itself. So it's not really a fixed load. It's just something that happens. You're going to lose heat, but as it loses heat to that chase that it's in, then the temperature differential is going to become less, and it's that delta T that drives the heat. So there's really not a whole lot of need for a whole lot of head and a whole lot of GPM. You basically have to measure the system out and figure out what you're going to need. I use a factor of about a ½ gallon per minute maximum through a ½ inch circulation return, but it's all going to be limited by whatever the common size of the main return coming back is going to be. But these pumps basically have the ability to be able to look at the pressure differential, and they don't care what's open, they don't care what's closed, they just know that they're supposed to maintain this pressure differential. So as these valves start pinching closed, and by the way, the Series 116 valve will never close off 100%. It closes way down, but it does not stop flow completely, so it keeps minimum flow going through that system. And basically the pump sees that, it goes, oh, whoa, look, there is no demand right now. I'm generating plenty of pressure differential, and there's really no need for any gallon per minute flow, so it lowers its RPMs to maintain whatever pressure differential you've programmed it for. And as the valves start opening, It sees that drop in pressure and goes, oh, I need to increase my RPMs to be able to stay up with that load. But these systems, basically, you set them up, it's not going to be a bang bang type situation, whether it's either on or it's off. It's modulating. You have a modulating boiler at the bottom of the system that's modulating its heat input to the actual storage tank itself. You have a distribution system that has modulating valves on the circulation returns, and you have a pump that can see that modulates its RPMs based on the pressure differential that it's trying to create. And the thing that we don't take into consideration on these systems is the fact that we've also got gravity working in our advantage. Hot water rises, cold water settles. I've actually designed some systems before that had no pump on them whatsoever. It was all gravity circulation. I used a Venturi fitting on the cold water inlet to the system with the side branch tied to the circulation return, so that anytime anybody was drawing any hot water in the system, it essentially enhanced the natural circulation that was occurring within the system itself. But unfortunately, the code authorities have decided that gravity is illegal. They will not allow a gravity circulation return system. And I'm thinking, what's wrong with using a zone valve to stop the flow during periods of non-use, and then open that zone valve and allow gravity circulation to occur again during periods of use? And basically, that's one of the uphill battles that we're trying to fight on these things. But that gravity is huge as it pertains to circulation within these systems itself. So, if you thought that this certain size of pump was probably adequate, you could probably drop one size of pump and still be in a very good, safe condition. There's really no need to move water at a high velocity through these systems.
Thanks, Mark. We had another question here too, and they talked about temperature differential, and they mentioned what temperature differential, if any, should you set the thermal balance valve and the temperature of the variable speed pump. And we've run into this, I'll kind of give my 2 cents and let you, let's hear what you think too. But like, we've had a lot of manufacturers of circulators that have a temperature sensor on it. So the idea is that it throttles back and forth based on its own thing, doing its own thing with its own sensor. The idea, though, is that if you have these thermal balancing valves, in my opinion, at each riser or each branch or anything like that, let them do the work. Set your circulator to a differential. You agree the same thing? Just set it to a fixed differential and go from there.
I agree. What the pump can't see is how the system was piped. Was it piped parallel reverse return, or was it piped parallel direct return? Yep. And once it sees that return water temperature coming back, then it lowers its RPMs, going, yeah, hot water is here. Well, It may be there, but it's not at the furthest point of use in that system itself. And the only way that you can address that is by using a Series 116 thermal balancing valve and let that pump to a pressure differential. Get rid of the temperature. It's not its function. Its function is create a pressure differential. It's going to cause flow within the system itself. Temperature is not its responsibility. Temperature is the source of supply, the mixing valve, and the balance of thermal balancing valve's responsibility. All that pump needs to do is make a pressure differential, and that's really all these pumps are, is a pressure differential machine. What it does as it pertains to GPM is another function. Are all the valves open? Are all the valves closed? And I agree with you. There are so many different systems that are out there. I having been at this for 49 years, I've seen some of the systems that are out there, and there's some interesting systems. I know there's some domestic hot water systems. I think it's called DMAND, demand, that basically has an occupancy sensor. It's a motion sensor that when you walk into the bathroom, it goes, oh, you're there, and it turns on the pump. Well, that's great. I walked in to blow my nose. What the hell did you turn the pump on for?
Yeah.
If I want hot water, I should push a button and say, I need hot water. And then you get hot water in a relatively short period of time. And, they've got pumps that basically will pump the hot water back through the cold water line back down to the source, which is great if you don't have a dedicated circulation return line. But you're also going to be in a situation where you are technically flushing hot water down the drain, and that doesn't make any sense. So I look at these systems and it's like, okay, what's the ultimate high efficiency, common sense, best systems that are available? And it basically comes down to the same package that we've basically addressed, which is having a good source of supply, high efficiency, use reverse indirect. And by the way, there are more than one manufacturer of reverse indirects on the market these days. I know that Lochinvar just brought one out recently. I haven't had a chance to check the specs, but the price is right. And You know, it's a different world. I mean, we're used to the old storage tanks with a small heat exchanger that required an extremely high approach water temperature from the heat source to be able to kick heat into the storage tank. Well, that's all going away. You need to adapt to the new technology that's available. If you want to use a modulating boiler, a condensing boiler for your high efficiency domestic hot water heating production, you need the benefit of the surface area of the reverse indirect, which will allow you to operate that boiler at roughly 10 degrees hotter than your desired target water temperature inside the storage tank itself, and basically set these systems up so that they are as efficient as possible. You only circulate the hot water that's necessary to satisfy the demand. I don't really believe in putting a timer onto a system, because you can't dictate to people when they can and cannot use hot water heating systems. In an apartment complex, you've got people working 3 different shifts. So why do you give preference to the people that work from 6 in the morning until 6 o'clock at night, as opposed to the people that start at midnight and they've got to wait for hot water? So if you keep the system in a constant, ready, steady state and basically control the flow based on temperature of availability at the furthest point of use, then you're doing the best that you can possibly do. Insulate the lines, heck yeah, do that. These situations where we get into these older buildings where they're experiencing hydraulic erosion because they had a 1.5 horse pump and a circulation return, then our recommendation is to go to PEX. If you go to a cross-linked polyethylene tubing, it has a lower heat transfer coefficient than copper tubing would. You insulate it, you reduce your losses, you basically set these systems up so that they're thermally as efficient as they can possibly be.
Yeah, and I think you made a really great point there too, Mark. The fact is, we talked about the temperature sensor on that pump. The pump only cares what water the temperature is that right there at the pump, if it's got one, and it has no idea if there's the water's taking the path of least resistance out in the distribution system. If it's seeing hot water because one riser's coming back faster, it doesn't know what all the other risers are doing. And like you said, it needs to do its job to create a differential and let the balancing valves do their job.
Yeah.
That I think is awesome.
Yeah, water's like my ex-brother-in-law, wet, lazy, and stupid.
Yeah, I love that one. That makes me laugh every time. And you're 100% correct. It wants to take the path of least resistance, and we got to make it go where we want it to go. And understanding why it's doing what it's doing, I think, is half the battle, and not just a means of you need a higher temperature in your tank or a bigger pump or whatever. One last question before we hit the road here, and there's a couple of more questions in here, but I think you guys had great questions from the webinar. I want to commend you on that. There's some really good ones in here, but some of them are going to take a little bit more time that we don't have right now, but we will definitely get to every one of your questions for sure. But the one last one that I wanted to talk about is, you mentioned about you usually design your recirc systems around 3 feet per second velocities. Is that typically using copper, or what materials are you using? The only reason I ask is because PEX is usually a little bit different of an animal. Usually they're looking for less velocity on constant recirc.
Yeah, my assumption is that it would be a copper system, which the limitation of 3 foot per second for hot water that's bearing a lot of oxygen is a recommended practice. As it pertains to PEX tubing itself, there's a whole lot of stuff that people need to understand about that. There's a number of, and I didn't know this myself. I didn't realize that, I knew they put an antioxidant package into the PEX when they extrude it, but I didn't take into consideration the fact that the water company is also putting oxidizers into it in the form of chlorine, and that it has a tendency to break down the anti-oxidizer package within the system itself. So anytime we get into a situation where we're recommending the consumer replace their copper lines with PEX for the circulation return lines, then we recommend that they use the higher resistance abilities, the higher antioxidant package, so that we don't put ourselves into a scenario where 20 years from now we go, oh, I didn't know that. Gee, wish I'd known then what I do now.
Yeah, and there's a number of them, where they, they'll list velocities saying, they can handle these really high velocities, but then in the kind of the fine print, it'll say something to the effect that, with constant recirculation systems, only go to this velocity instead, so just, be mindful, is basically is what I'm getting at. Be mindful of your materials that you're using in that system, and, follow the rules, because like you said, you don't want to get bit in the butt 10 or hopefully maybe 10 years, maybe it could be sooner. You know, you don't want to get bit in the butt at any point, especially on a system that that should be working for a good long time.
Yeah.
So.
Having been doing this for 49 years, I look back at stuff that I was doing 49 years ago. What were you thinking?
if I knew then what I know now, yeah, I always think to myself the same exact thing, Mark. So, all right, guys.
That's why I love to pay it forward to people, let them learn from my experiences, and hopefully avoid them making the same mistakes that I've had. And again, I appreciate Caleffi and the team behind the scene that puts this whole thing together and pays it forward to the industry and upward and onward.
All right, perfect. Well, thanks again, Mark. We've got a little video clip at the end here. Max is going to take over everything here. And just want to remind everybody that, again, if you have any questions that didn't get answered today, we'll definitely get to those from there. Thank you again, Mark, for your time and your experience and your knowledge. And it is greatly appreciated. And I hope you enjoy the rest of your day.
I will. Thank you.
Thanks.